Light has always occupied a strange position in human thought. It is at once ordinary and mysterious, present in every moment of vision, yet resistant to complete explanation. From ancient philosophy to modern physics, light has served as both a tool for understanding the universe and a symbol for understanding itself. Long before modern science, thinkers struggled to describe what light truly is. Some believed it to be a stream of tiny particles emitted from luminous objects. Others argued it must be a wave, spreading through space like ripples on water. These early debates were not merely technical disagreements. They reflected deeper questions about reality, causality, and the limits of human knowledge. By the 17th century, scientific experimentation began to sharpen these philosophical intuitions. Isaac Newton, through careful study of prisms, concluded that white light is composed of many colors, and proposed that light behaves as a stream of corpuscles, or particles. Newton's theory was powerful, mathematically precise, and successful in explaining reflection and refraction. At the same time, Christian Huygens developed a competing wave theory. He suggested that light propagates through space as a vibration, much like sound travels through air. This wave model elegantly explained diffraction and interference, phenomena that were difficult to reconcile with Newton's particle picture. For more than a century, these two perspectives coexisted in tension. The question was not merely which theory worked better in practice, but what light truly is in its fundamental nature. Is it composed of discrete objects, or is it an extended motion? Does it behave like matter or like a field? By the 19th century, wave theory gained strong experimental support. Thomas Young's double-slit experiment revealed interference patterns that seemed unmistakably wave-like. Later, James Clerk Maxwell unified electricity and magnetism into a single theory and demonstrated that light itself is an electromagnetic wave. Light, in this picture, required no particles at all. It was an oscillation of electric and magnetic fields traveling through space at a fixed speed. For a time, it appeared that the mystery had been resolved. Light was a wave, governed by Maxwell's equations, moving smoothly and continuously through the electromagnetic field. Yet beneath this apparent clarity, unresolved questions remained. One problem concerned how light exchanges energy with matter. Classical physics predicted that hot objects should emit infinite energy at short wavelengths, a prediction famously known as the ultraviolet catastrophe. This absurd result signaled that something fundamental was missing from the classical picture. At the dawn of the 20th century, Max Planck proposed a radical solution. Energy, he suggested, is not emitted continuously, but in discrete packets, later called quanta. This idea challenged the assumption that nature is smooth and uninterrupted at all scales. Energy appeared to come in steps, not in a continuous flow. Albert Einstein soon extended this insight. In explaining the photoelectric effect, he argued that light itself behaves as if it consists of individual particles, later called photons. These photons carry discrete amounts of energy and can eject electrons from metals only if their frequency exceeds a certain threshold. This discovery revived the particle nature of light in a new and unexpected form. Light, once understood as a wave, now displayed unmistakable particle-like behavior. Yet it still produced interference and diffraction, hallmarks of wave motion. The result was a deep conceptual crisis. Light could not be fully described as either a classical particle or a classical wave. It exhibited properties of both, depending on the experimental arrangement. The more carefully physicists studied light, the more it resisted being forced into any single classical category. It is within this intellectual landscape that Niels Bohr made his most influential contributions. Bohr did not merely seek to solve equations. He sought to clarify the meaning of physical concepts themselves. His concern was not only what the mathematical formalism predicted, but what it implied about the nature of reality and the limits of description. Before turning directly to light, Bohr first confronted a related problem in atomic structure. Classical physics predicted that electrons orbiting a nucleus should continuously radiate energy and quickly spiral inward, causing atoms to collapse. Yet atoms are stable. Matter persists. The classical theory could not account for this stability. Bohr proposed that electrons occupy discrete, quantized orbits and emit or absorb energy only when jumping between them. These transitions produce light at specific frequencies, giving rise to atomic spectral lines. Once again, light appeared not as a smooth, continuous emission, but as a quantized phenomenon tied to discrete changes in atomic states. This model was an early step toward quantum theory, and it revealed a deeper principle: the behavior of light cannot be separated from the structure of matter. The properties of radiation depend on the quantized nature of atomic systems. As quantum mechanics developed further, the dual nature of light became impossible to ignore. Experiments showed that single photons passing through a double slit can create an interference pattern over time, as if each photon interferes with itself. Yet when measured at a detector, each photon arrives as a localized, particle-like event. How can something behave like a spread-out wave and yet appear as a single, indivisible particle? This is not merely a technical puzzle. It forces us to reconsider what we mean by existence, measurement, and physical reality. Bohr approached this dilemma with a distinctive philosophical stance. Rather than insisting that light must be either a wave or a particle in itself, he argued that these descriptions are complementary. Each is valid within a specific experimental context, but neither alone provides a complete account. According to Bohr, the behavior of light cannot be discussed independently of the conditions under which it is observed. The experimental setup determines which aspects of light become manifest. In one arrangement, interference appears and the wave description is appropriate. In another, discrete impacts are recorded and the particle description becomes necessary. This idea became known as the principle of complementarity. It suggests that certain properties cannot be simultaneously defined with arbitrary precision, not because of technical limitations, but because of the fundamental structure of nature. In Bohr's view, physics is not a direct mirror of an underlying objective reality independent of observation. Instead, it is a framework for organizing and communicating what can be said about experiments. The goal is not to uncover a final, classical picture of what light is in itself, but to understand the conditions under which different descriptions apply. This philosophical shift marked a turning point. Light was no longer a simple object with fixed properties. It became a phenomenon whose character depends on the relationship between system and observer. Yet Bohr did not claim that nature is arbitrary or subjective. On the contrary, he insisted on strict logical consistency and empirical discipline. What he rejected was the idea that classical concepts, such as particle and wave, could be uncritically extended into the quantum domain. Light, in this new understanding, stands at the boundary between the classical world of everyday experience and the quantum world of atomic events. It reveals both the power and the limits of human conceptual frameworks. Even today, physicists continue to debate what light truly is. Is the photon a particle? Is the electromagnetic field the more fundamental entity? Does light exist as a wave of probability until measured? Or do these questions themselves rest on outdated assumptions? What Bohr discovered about light is not only a set of technical results, but a deeper lesson about knowledge. Light teaches us that nature may not conform to the categories we find most comfortable. It may require new forms of reasoning, new languages, and new philosophical humility. In this series, we will explore what Bohr discovered about light that still confuses physics today. We will examine how light behaves in quantum experiments, why it resists classical explanation, and what its strange nature reveals about reality itself. In the next part, we will move from historical foundations into a deeper scientific explanation of how quantum theory describes light, and why Bohr believed that understanding light requires rethinking the very meaning of measurement and physical description. To understand what Niels Bohr truly uncovered about light, we must move beyond historical narrative and enter the structure of quantum theory itself. Here, light is no longer described as a simple wave or a simple particle, but as something that obeys deeper, more abstract laws. At the center of this transformation is the quantum description of the electromagnetic field. In classical physics, light is represented as a continuous wave of oscillating electric and magnetic fields spreading smoothly through space. Its energy can take any value, and its intensity varies continuously. Quantum theory overturns this assumption. It states that the energy of light is quantized. Light is emitted and absorbed in discrete units called photons, each carrying an energy proportional to its frequency. This proportionality is expressed by Planck's relation, where energy equals Planck's constant multiplied by frequency. This means that low-frequency light carries small packets of energy, while high-frequency light carries larger ones. There is no such thing as half a photon or a fraction of a photon. Light interacts with matter in indivisible steps. Yet the photon is not a particle in the classical sense. A classical particle has a definite position and trajectory at every moment. A photon, by contrast, is described by a quantum state, which encodes probabilities rather than certainties. When light propagates through space, it does not travel along a single, well-defined path. Instead, its quantum state spreads out, allowing multiple possible paths to contribute to its behavior. This spreading is what gives rise to interference patterns in experiments such as the double-slit experiment. If light were merely a classical particle, it would pass through one slit or the other, producing two distinct impact regions. Instead, even when photons are sent one at a time, the final pattern shows alternating bright and dark bands. This pattern arises from the superposition of probability amplitudes, a mathematical structure unique to quantum theory. In this framework, a photon does not choose a single path in advance. Rather, all possible paths contribute to the final outcome, and their contributions can reinforce or cancel one another. The interference pattern is not produced by particles colliding with one another, but by the self-interference of each individual photon's quantum state. At the moment of detection, however, the photon appears at a single, localized point. The wave-like spread of probabilities gives way to a particle-like event. This transition from a distributed quantum state to a definite detection outcome is one of the deepest puzzles in physics. Bohr addressed this puzzle not by attempting to describe what happens in hidden detail, but by focusing on what can be meaningfully said about experiments. He argued that the concepts of wave and particle are not properties that light possesses simultaneously in a classical sense. Instead, they are complementary descriptions that apply under different experimental conditions. If an experiment is designed to reveal interference, light must be described as a wave-like phenomenon. If it is designed to reveal discrete impacts, light must be described as a particle-like phenomenon. Attempting to force both descriptions into a single classical picture leads to contradiction. This is closely related to the uncertainty principle. In quantum mechanics, certain pairs of physical quantities cannot be known with arbitrary precision at the same time. Position and momentum are one such pair. If we try to localize a photon's position very precisely, its momentum becomes uncertain, and vice versa. This uncertainty is not due to imperfect instruments. It arises from the fundamental mathematical structure of quantum states. The more we constrain one property, the more we necessarily blur another. Bohr interpreted this as a limitation on what can be simultaneously defined, not merely what can be measured. In his view, quantum theory does not describe a fully detailed underlying reality hidden behind observation. Instead, it provides rules for predicting the outcomes of experiments within the limits imposed by complementarity. Consider polarization, another key property of light. Classically, polarization describes the orientation of the electric field oscillation. Quantum mechanically, polarization becomes a property of individual photons. A photon can exist in a superposition of polarization states, meaning it is not strictly horizontal or vertical until measured. When a photon passes through a polarizing filter, it is not simply filtered like a classical wave. Instead, its quantum state is projected into one of the allowed polarization states, with probabilities determined by its initial superposition. This projection process exemplifies how measurement changes the state of light. Measurement does not merely reveal a pre-existing property, it actively participates in defining the outcome. Bohr emphasized that the measuring apparatus must be described in classical terms. The pointer on a detector, the flash on a screen, or the click in a counter must have definite outcomes if communication and scientific discourse are to remain meaningful. Quantum uncertainty applies to the microscopic system, but the macroscopic recording device must yield a definite result. This requirement introduces a conceptual boundary between the quantum system and the classical measuring device. Light, as a quantum entity, obeys probabilistic laws, but the record of its behavior appears as a definite classical event. Bohr did not claim to know the underlying mechanism that produces this transition. Instead, he argued that quantum theory sets fundamental limits on what can be coherently described. Any attempt to describe the detailed behavior of light between emission and detection must remain consistent with the constraints of complementarity. Modern experiments have pushed these ideas even further. In delayed choice experiments, the decision to observe wave-like or particle-like behavior can be made after the photon has already entered the apparatus. The outcome still conforms to the chosen measurement setup, suggesting that light does not carry a fixed identity independent of experimental context. In quantum entanglement, pairs of photons can be created in correlated states such that measuring one instantaneously influences the predicted outcome of the other, regardless of distance. Light here becomes part of a non-local quantum structure that defies classical intuitions about separateness and independence. Bohr's response to such phenomena was not to deny their strangeness, but to insist on logical restraint. Quantum theory, he argued, does not require us to abandon causality or rationality. Instead, it requires us to abandon the assumption that all aspects of physical reality can be simultaneously described using classical concepts. In technical terms, the quantum state of light is represented by a wave function, or more generally, by a quantum field. This mathematical object encodes all possible outcomes and their probabilities. It evolves deterministically according to quantum equations, yet yields probabilistic results when measured. This dual structure, deterministic evolution combined with probabilistic measurement, lies at the heart of the mystery. Light follows precise mathematical laws, yet individual events appear random. The theory predicts statistical patterns with extraordinary accuracy, but it does not predict the exact result of any single photon detection. Bohr saw this not as a flaw, but as a feature. He argued that demanding complete predictability of individual events reflects a classical bias that may not apply at the quantum level. Nature, in this view, is not obligated to conform to our expectations of determinism. Thus, what Bohr discovered about light is inseparable from what he discovered about knowledge. Light reveals that our descriptions of reality depend on the conditions under which observations are made. It shows that the act of measurement is not passive, but an integral part of the phenomena we observe. In the next part, we will explore what this means. We will examine the philosophical implications of Bohr's interpretation, how light reshapes our understanding of reality, and why its strange behavior continues to challenge physics and human intuition. By the time Niels Bohr had fully articulated his ideas about light, the problem was no longer confined to physics alone. It had become a problem about meaning, knowledge, and the limits of human understanding. Light, once thought to be a simple physical entity, had become a mirror reflecting the structure of thought itself. At the heart of this transformation is a profound realization: light cannot be fully understood as an object with fixed, observer, independent properties in the classical sense. Instead, its behavior depends on the experimental context in which it is studied. This dependence forces us to rethink what it means to say that something is real. In classical physics, reality is assumed to exist in a fully determinate way, regardless of whether it is observed. A particle has a position and a velocity at all times. A wave has a definite amplitude at every point in space. Observation merely reveals what is already there. Bohr argued that this assumption breaks down at the quantum level. Light does not carry a complete set of classical properties waiting to be uncovered. Rather, what can be meaningfully said about light depends on how we choose to interact with it. If we design an experiment to reveal interference, light behaves in a wave-like manner. If we design an experiment to detect localized impacts, light behaves in a particle-like manner. These are not two simultaneous properties of a hidden underlying object. They are two complementary ways of describing phenomena that cannot be unified into a single classical picture. This insight challenges the idea that physics should aim to describe reality as it is in itself. Instead, Bohr proposed that physics should describe what we can say about nature under specific experimental conditions. The goal is not to eliminate ambiguity by forcing nature into familiar categories, but to respect the limits imposed by quantum structure. Light thus becomes a lesson in epistemic humility. It teaches that some questions, though natural from a classical standpoint, may not have meaningful answers within the framework of quantum theory. For example, one might ask which slit a photon really passed through in a double-slit experiment, even when no measurement was made. Bohr would argue that this question assumes a classical notion of trajectory that is not applicable in that context. If the experiment is set up to reveal interference, then the concept of a definite path simply does not apply. This is not because the answer is unknown, but because the question itself relies on concepts that lose their meaning outside certain conditions. The same reasoning applies to the idea of wave function collapse. Many interpretations of quantum mechanics attempt to explain what physically happens when a photon is detected. Does the wave function suddenly collapse? Does reality split into multiple branches? Is there an underlying hidden mechanism? Bohr resisted such speculative additions. He maintained that quantum theory already provides a complete description of what can be predicted and communicated. Introducing unobservable mechanisms, he argued, risks reintroducing classical assumptions that quantum theory has already shown to be inadequate. Light in this view is not mysterious because it hides a deeper classical reality. It is mysterious because our classical ways of thinking are not sufficient to capture its behavior. This has profound implications for how we think about causality. In classical physics, causes precede effects in a continuous, deterministic chain. In quantum experiments involving light, however, outcomes can depend on measurement choices made after the photon has already entered the apparatus. In delayed choice experiments, whether light exhibits wave-like or particle-like behavior can be determined after it has effectively passed the region where such behavior would normally be decided. This challenges the idea that light carries a fixed identity through time. Bohr would say that such paradoxes arise only if we insist on attributing definite properties to light independent of measurement. If instead we accept that properties are defined only within specific experimental contexts, the apparent contradiction dissolves. Light also forces us to reconsider the nature of objectivity. In everyday life, objectivity means describing things as they are, independently of who observes them. In Bohr's framework, objectivity means something different. It means that experimental results can be unambiguously communicated using shared classical language, even if the underlying quantum phenomena resist classical visualization. The measuring device plays a crucial role here. While light itself is governed by quantum laws, the apparatus that records its behavior must yield definite outcomes. The pointer must point to one value. The detector must click or not click. The screen must show a specific pattern. Bohr insisted that the classical description of measurement devices is not optional. It is necessary for science to remain a coherent enterprise. Without definite outcomes, there would be no stable basis for communication or agreement. Thus, light exists at a conceptual boundary. On one side lies the quantum world, governed by probability amplitudes and superpositions. On the other side lies the classical world, where events are recorded as definite facts. Light bridges these worlds, revealing both their connection and their tension. This boundary has inspired countless philosophical debates. Does light exist as a physical entity independent of observation, or only as a set of potential outcomes? Are photons real particles, or merely convenient mathematical constructs? Is the electromagnetic field more fundamental than the photon, or vice versa? Bohr would caution against treating these questions as if they had simple, definitive answers. He would emphasize that our concepts are tools, not mirrors of ultimate reality. Their validity depends on the context in which they are applied. Light also reshapes our understanding of determinism. In classical theories, complete knowledge of the present implies complete predictability of the future. In quantum theory, even complete knowledge of the quantum state yields only probabilistic predictions for individual events. A single photon detection cannot be predicted with certainty. Only the statistical distribution of many detections can be predicted. This randomness is not due to ignorance, but appears to be an intrinsic feature of nature. For some, this undermines the idea that the universe is governed by strict laws. For Bohr, however, it simply reveals that the laws of nature operate at a deeper level than classical determinism. The regularity lies in the structure of probabilities, not in the outcomes of individual events. Light therefore teaches that lawfulness and unpredictability can coexist. Nature can be orderly without being fully deterministic in the classical sense. Another implication concerns realism. Many scientists and philosophers want to believe that physical theories describe an underlying reality that exists independently of observation. Bohr did not deny reality, but he challenged the idea that it can be fully described using classical categories. In his view, quantum theory does not tell us what light is in itself. It tells us how light behaves in relation to experimental arrangements. Reality, then, is not a fixed collection of properties, but a structure of possible phenomena constrained by the laws of quantum mechanics. This perspective does not diminish science. Instead, it clarifies its scope. Science becomes not a quest for a final picture of what the world is, but a disciplined method for organizing and predicting experiences. Light stands as one of the clearest demonstrations of this shift. Its dual nature, its sensitivity to measurement, and its resistance to classical visualization reveal the depth of the conceptual revolution initiated by quantum theory. Even today, physicists struggle with the implications of Bohr's insights. Competing interpretations of quantum mechanics attempt to restore a more classical sense of realism or determinism. Yet none has achieved universal acceptance. What remains undisputed is that light continues to challenge our most basic assumptions. It forces us to ask not only how nature behaves, but how we should think about nature. In the final part, we will step back and reflect on the broader meaning of Bohr's discoveries about light. We will consider why this mystery persists, what it reveals about the limits of human understanding, and how it shapes the future of physics and philosophy. Light remains one of the most revealing and unsettling subjects in all of physics. After more than a century of quantum theory, it still resists any single, intuitive explanation. This persistence is not a failure of science. Rather, it is a sign that light exposes something fundamental about both nature and the limits of human understanding. What Niels Bohr ultimately discovered about light is not merely that it behaves in strange ways. He revealed that the very framework through which we describe reality must change when we confront the quantum world. Light does not simply challenge old theories. It challenges old ways of thinking. In classical physics, we expect that every physical object has well-defined properties at all times. We imagine that if we knew enough, we could trace a complete and continuous history of its motion. Light breaks this expectation. It cannot always be said to have a definite path, a definite form, or a definite identity independent of how we observe it. Bohr's response was neither to deny reality nor to mystify it. Instead, he proposed a disciplined humility. He argued that our concepts are shaped by experience in the macroscopic world, and that these concepts cannot always be extended without modification into the quantum domain. When we attempt to do so, we generate paradoxes that arise from our language rather than from nature itself. Light teaches that different descriptions may be necessary to capture different aspects of the same phenomenon. Wave and particle are not competing truths, but complementary tools. Each reveals something real, but neither alone can exhaust the full character of light. This lesson extends beyond optics and quantum mechanics. It suggests that knowledge itself may be inherently contextual. What can be meaningfully said depends on the conditions under which questions are asked and observations are made. In this sense, light becomes a philosophical guide. It reminds us that certainty is not always attainable in the way classical thought once promised. Yet it also demonstrates that uncertainty does not imply chaos. Quantum theory predicts the behavior of light with extraordinary precision, even if it cannot predict the outcome of each individual event. The mystery of light also continues to shape modern physics. Advances in quantum information, quantum computing, and quantum communication rely on the very features of light that once seemed paradoxical. Superposition, entanglement, and probabilistic measurement are no longer seen merely as conceptual problems. They are now practical resources. Photons carry quantum information across vast distances. Entangled particles challenge classical notions of separability. Experiments continue to probe deeper into the boundary between quantum possibility and classical reality. Yet with each new discovery, the conceptual questions return in new forms. Does light reveal an underlying reality beyond our current theories, or does it mark a permanent limit on what can be known? Are future physical frameworks likely to restore a more intuitive picture, or will they further distance us from classical imagery? These questions remain open. Bohr would likely remind us that progress in physics does not always mean moving closer to a simple, final picture of reality. Sometimes progress means learning to live with conceptual tension while preserving logical coherence and empirical clarity. Light endures as a symbol of this tension. It is both physical and conceptual, both measurable and elusive. It obeys precise mathematical laws while defying simple mental images. It illuminates the universe while revealing the shadows in our understanding. Perhaps the deepest insight Bohr left us is that the purpose of physics is not to strip nature of mystery, but to clarify where mystery genuinely resides. Light shows us that some mysteries are not temporary gaps in knowledge, but permanent features of the relationship between observer, theory, and world. In this way, the confusion surrounding light is not merely a technical challenge. It is a philosophical invitation. It invites us to refine our thinking, to recognize the limits of intuition, and to appreciate the subtlety with which nature presents itself. Light continues to confuse physics because it continues to teach physics. And in that teaching lies its enduring power, not only as a subject of science, but as a guide to deeper understanding.